Hi everyone, this is one of the most important lecture in semiconductor fundamental. So in this lecture we are learning how we move from atom to band. Okay, first we will learn what is quantization concept, then semiconductor model, bonding, what is happening at atomic level, what is happening at energy level, and carriers, how you do show carrier in energy band model and in bonding model, and then how you classify material based on energy band gap. Okay, we will discuss one by one. So directly jumping to silicon is maybe a bit difficult. That's why I have taken hydrogen atom. It is a simple atom which is having one proton and one electron. They are attracted due to Coulombic force. So this is the formula that we have learned in intermediate, okay, 12th course physics. So this is n is orbital number or orbital identifier. So higher the n, lesser the binding force between them. Obviously from Coulomb force you can have idea higher the distance, lesser the force, because it is inversely with force varies. Okay, so if electron is in second orbital, in case of hydrogen it's not there, but suppose we are discussing different atom. So if electron is in second orbital, the binding energy between this electron and nucleus is bit less in comparison to this orbital and nucleus. Okay, now we will move towards silicon. So what is silicon is having atomic number 14. This is orbital configuration. So 1s2. So how many electron can reside in s orbital? 2 only, with different spin. That also means this is energy axis. They have very little difference between energy, because from Pauli exclusion principle, no two electron has same position and momentum. So if you are saying they have same kind of position, then they have should have different momentum, but they have bit energy difference as well, but very less. So we will show them at the same energy, because really what Pauli said is no two electron has same energy. So 1s2, 2s2, and this is second orbital. How many electron can reside in second electron? 8. 2 in s, 6 in p. And how many can reside in third orbital? But how many electron are left? 4. So 2 goes here and then 2 goes here. And how many states are vacant? 4. Balance, vacant state. We can say vacant state. Okay, so this is outermost orbital. Okay, we will discuss one by one. Okay, suppose this is one of the important thing I want to tell you. Suppose one electron jump from higher orbital to lower orbital. Okay, then it will release a photon which is having energy E4s minus E3. Okay, so E4s minus E3p, the difference, the energy that photon will release, because this electron is higher energy, is jumping here, so it should release the energy, that much energy in terms of photon. Okay, so this is one of the most important thing. Suppose this is we have drawn for isolated silicon, but when we are making atom, there are a lot of silicon atoms, around 10 to the power 23 atoms per centimeter cube. It's too much. Okay, it's a lot of electrons are there. So how they will interact, this is very important. So whatever is interaction, affection, or anything, you can say all dramabazi is happening here only at the outermost orbital. Okay, so what is outermost orbital is? And this is called as core. So they are very much binded with atom. So they are not going to feel any force or any kind of reaction or bonding. Everything is going to happen at these outermost orbital. It has 4 valence electron, 8 states are there, because 6 state in p and 2 in s. The total states, how many states? 8. How many fit? 4 valence, 4. So what is outermost orbital is called as valence. So 4 valence electron are there and 4 vacant states are there. Total 8 states are there. 4 are valence, filled with valence electron, and 4 are vacant. Okay, these are core levels. It has atom plus core electrons. So what is semiconductor models? So two kind of models are there. One is bonding model, okay, that we are discussing here. Which is like, if you want to know what is happening at atomic level, you need to understand bonding model. And second one is energy band model. Energy band model. And what is happening at energy level, you need to understand energy band model. But in a larger picture, energy band model is like applicable to everywhere, because you can't draw like this configuration to the dimension. This is not very accurate as well, because it is a 2D picture only. So you can't draw for every atom, okay, but for taking idea initially is very beneficial. So bonding model is very important for understanding what is happening at atomic level. So what is this atom is represented is like, it is having atom plus 1s2, 2s2 and 2p6 core level electrons. Okay, and what are the other electrons? 4 electrons are at a balanced electron. So 1, maybe 2 or 3 and 4. And these are like 4 electrons it is sharing from neighboring atom. So how many electrons feeling? It has 8. So it can be stable. That's the reason they are doing covalent bonding. Okay, you understood? So this is like, when we are showing this bond, this is showing one valence electron. Shared valence electron is written here. Shared valence electron, one electron. If this breaks, that means one electron is free to move. You need not to confuse. One line means one electron is shared, either by this electron or either by this. Suppose this is electron you are seeing from this atom, okay, A1, one electron, then this electron should be from this atom, A2, okay. So this from this atom, 1, and this is from this is from maybe this, and this is from other. So this, it will feel like it has 8 electrons, okay. So suppose this bond is broken. So this is broken bond, electron is free to move. That electron is called as electron is moving in conduction band, okay. That electron is called as electron is moving in conduction band. And there is a vacancy. Now here electron can come because it's vacant place. So suppose this electron come this place, and then there is a vacancy here, and this electron come to this place and vacancy is here. So you understood, if bond is broken, electron is moving like this, electron are moving like this, and hole is moving like this. Suppose this electron come here and this electron come here. So electron is moving like this, hole is moving like this in opposite. So electron is having negative charge, as we know. So that means hole is a particle which is having positive charge. That is very important. So from this diagram we understood like electron is having a negative charge and hole is having positive charge. Okay, got it? So second is like, what is energy band model? So this is very important. Okay, I am telling you in a very simplistic way. So silicon atom is having 14 electrons. So we are taking only valence electron 3s2 3p2. So what Pauli told us, like no two electron having same energy. So it is isolated atom. You have like bit like gap here. Okay, it's all right. But how many electrons I told you in a how many atoms in a when you are making a material, how many atoms are there? 10 to the power 23 atoms per centimeter cube, and 10 to the power 23 atoms. How many electrons? 4 into 10 to the power. It's too many electrons. Okay. So how you satisfy this Pauli's rule? So this like discrete level will become continuous. So like these are continuous line will become when you are making like localized to delocalized. Localized means isolated. Isolated. Here it is becoming like material. So this is not isolated. 4 into 10 to the power 23 electron. Here only 4 electron. Okay, per centimeter cube. So what will happen? These are like continuous band. And how many states are there? 8 states. This always remember, because cis 6 states are here, 2 states are there. How many filled? 4. 4 filled electron or balanced electron. How many vacant? 4 vacant. So if there are n atoms, so how many states? 8 n states. 4 n filled, 4 n vacant. So all filled states come here, and all filled states are here. 4 n filled and 4 n vacant. Those states who are vacant is called as, that band is called as conduction band. Those who are filled is called as valence band. And then there is a reason like this become a forbidden gap. You can follow like Benjamin Stickman. This is very good book to understand, or R.F. Pierre to understand like full thing what's happening in the picture. I am telling you quite a good way to understand in a simplistic manner. So then there is, these states are not allowed to filled by electron. There can't be any electron and hole. That's why it's called as forbidden gap. And this is all can you say also called as band gap. This is like forbidden. You can't touch it. No electron and hole can reside. No, it's a no state. Okay. Suppose you increase the temperature. All states are filled. You increase the temperature, and some electron is having energy. They moved here. Now they are having like vacancy. Okay. So how you can understand this phenomena? I will tell you in a very simplistic way. Suppose a analogy I am telling you, 40 chairs are there in a room and 40 students are there. And student can move only in chairs. Okay. So can any student move here? No. Because there are 40 chairs and 40 students. Suppose there is this other room is here, room number 2. There is also 40 chairs. Okay. But all are vacant. But at the previous time when T is equal to 0 Kelvin, suppose room is, the gate is closed, no one is allowed to move. At T is equal to greater than 0 Kelvin, they are getting energies. That means you are allowed electron to move. So 2 electron moved here. Now 2 electron are moved here. Now how many places they can move? 38 places they can go. So it's a movement. Okay guys. So now how many electrons are there? How many students are there? 38, because to move there, and 40 chair. So 40 chair means electron means student are there, and 2 chair are vacant. So these student can move into this chair. When these student move to this chair, these student come into these places. So electrons are moving. So this is a kind of analogy. When we are saying 40 student, this means these 40 students are 40 valence electrons. When there is a place like vacancy, that is called as hole. So whenever we are saying hole, free hole, that means we are talking about hole in valence band. Whenever we are saying free electron, it means electron in conduction band. Okay, you are getting my point? So nobody like take this much energy to say free electron. Always people are saying electron. That means in conduction band. When we are saying hole, hole means we are talking about valence. Okay. So this is like what intrinsic semiconductor we will discuss later. So how engineer and scientist in semiconductor area draw their energy band diagram. So this is like forbidden band gap, which is called as energy gap. This is the energy difference between these two, and this is the like position. That means suppose this material is it will not be that much, but take it as 1 millimeter thick. So how these band are moving? Suppose this band can be go down like this band can go like this, conduction band. Okay, maybe a valence band, maybe this. So how with the position here may be different if they are moving as with the position. Okay, so these are constant. We will discuss later what will happen, but right now it is important to take it as a constant. So nobody is going to draw these bands, our limit or lower limit. So people will draw this valence band maxima. This is called as EV, and conduction band minima people will say EC. The difference between these two called as EC, the band gap. Okay. So how do you correlate band energy bond model and energy band model? Like bonding model and band model. So there is no carriers. No carrier means this is fully filled. That is like same analogy, 40 student, 40 chair. This is fully filled. There are a lot of chairs, but no student are here. So this is fully empty. So no carrier means no bond is broken. There is no energy. So it is same like it is at 0 Kelvin. Okay. 0 Kelvin is called as a absolute temperature. That means no electron has any energy because the thermal energy is KT, which is KT is at Kelvin. So KT means 0 at T is equal to 0 Kelvin. So suppose you have given some energy, T is greater than 0 Kelvin and one bond is broken. So if one electron is free to move, how can you show that electron in like energy band diagram? Okay, let's see. So you can show like electron in this valence electron move here. Okay, this is like this electron that in bond model you are saying this is in energy band model. In conduction band, electron is moving. Okay, so if there is a vacancy that we have already discussed, so that we will show by hole will move opposite to electron. Okay, how you classify materials based on energy band diagram. So these are the state no electron and hole can resides. If this difference is bit higher at room temperature we are talking about. Okay, so it is bit higher around 5, 6, 7, 8, 9, then it is called as insulator. Okay, so silicon dioxide is a standard oxide or insulator we can say. There are many uses you will see in MOSFET and other devices. What is metal? Metal are like there is no band gap between all states are allowed to move, or maybe very little band gap like around 0.2 or 0.4. They are also considered as metals. So what is means by metal? Because there are a lot of valence electrons are here. Okay, they all are filled here. They all are filled, but you can see there are vacancy. Empty states are there in empty states. Okay, this is like conduction band, so, or you can treat this as a valence band. So these electrons need no energy almost to move in conduction. So they will jump like hoop like this. And these are like metals. They will conduct very high. Okay, they are very high conductivity. So what is like semiconductor? What is the use of semiconductor then? Because you can make semiconductor act as an insulator, and the same material can act as a metal with different doping and different kind of things. We will see later. Initially, people thought about like semiconductor is having no use, but because of a lot of research, we can see semiconductor is one of the most important thing in the industry that we are seeing. Okay, so they having a energy band gap between insulator and metal. Okay, that is the biggest you can do. Like you can increase the band gap as well, or you can decrease the conductivity at the same band gap. You can do a lot of things. We will discuss later. Okay. So what is the summary? Electron and holes. But mainly electron near the top moves near the top of the valence band and near the bottom of the conduction band. That we are saying at the top of valence band. We will not say electron. Mainly hole move near the top of valence band. It's moving electron because this is valence band. Suppose this is vacancy and lot of electron are here. Okay, so electrons are moving here, but hole is moving. So we will now, because this will be confusing. If you are talking about electron is moving in valence band and same thing in conduction band, electron is moving, how will you define? You will say electron of valence band, it will be confusing. So people will say holes. That means they are moving in valence band. Electron means it's moving in conduction band. Current in a semiconductor is carried by electron in conduction band, hole in valence band. Then these are the most important thing about this lecture. Okay, so take care. Thank you.